So we're looking at the chloroalkali industry now, right? So the chloroalkali industry speaks to, well, chloro, chlorine, and some alkali, right? So we're going to be looking at something like that, the production of these two things, what we can use them for, right? The environmental impact and how we can actually mitigate these impacts, right? So let's start off with the first method, the diaphragm cell. All right, so here's just a general structure of the diaphragm cell. All right, what we're going to be using here is chlorine gas, right? And we have saturated brine. Brine is basically extremely saturated or extremely concentrated salt water, right? So we're going to be taking these two things and carrying it through an electrolytic process, right? We know that we have the anode and the cathode here, right? And we have the brine passing through a diaphragm that allows us to now rip hydrogen gas, right, from, well, hydrogen gas and chlorine gas, right, from basically what's happening here. Um, yeah, so we can rip hydrogen gas from the brine, right, and we can also produce sodium chloride, right? So that's what we're looking at. So the production of sodium chloride and the production of general hydrogen gas as a byproduct, right? So we're gonna have sodium hydroxide, sodium chloride. We can actually have the production of hydrogen gas as well, right? So mainly, however, right, we're gonna be looking at sodium hydroxide and hydrogen gas, right? So the leftover, we can have leftover sodium chloride, which is the brine, right? Salt from the brine, and we can also have some other excess components, right? But most likely, we're gonna be looking generally at caustic soda, right, and some hydrogen gas, right? So let's have a look at this. So the diaphragm cell and the electrolysis of brine. So this is the first part. So we know that diaphragm cell is generally the typical way we industrially produce chlorine gas, hydrogen gas, and sodium hydroxide. Right? So sodium hydroxide remaining in solution. So we produce chlorine gas at the anode, hydrogen gas at the cathode, and sodium hydroxide is generally remaining in the solution that we can take off. Alright? So we have that there. So the process involves electrolysis of brine, which is saturated solution of sodium chloride and water, all right? Using also a porous diaphragm between it. So a porous diaphragm separates the anode and the cathode compartments, allowing ion migration, but limiting production mixing or product mixing, all right? So we allow the ions to move across the diaphragm, right, where the products do not mix. So we have sodium chloride solution or brine coming in, right, at the titanium anode. We must know how to reproduce these diagrams, by the way. At the titanium anode, we would have chlorine gas being produced, right? And at the steel cathode, we have hydrogen gas being produced. And then we have some sodium hydroxide solution, right, that is taken off there. Sodium hydroxide that is contaminated with sodium chloride, all right? So we have this general thing. So you must be able to reproduce this diagram. You must be able to label it. All right. So the composition of the electrolytes, the ions in brine. So brine contains sodium and chloride ions from dissociation of sodium chloride. Right. It also contains hydrogen H plus and hydroxide ions. Right. From autoionization of water. So we have these four components here. So these four components will participate in the electrochemical and chemical processes at the respective electrodes. So at the anode, we have the chlorine or the chloride gaining. Is it gaining or losing at the anode? What do? We gain electrons or lose electrons? We lose electrons. Lovely. Lovely, right? So we have the anion, the chlorine anion or the chloride anion, losing electrons to produce chlorine gas at the anode. And then at the cathode now we have water, right, being split to produce hydrogen gas, right, and some hydroxide. So we have that there. So generally what's happening here now, right, we have the chloride that is going to be gaining, well, losing electrons rather to produce chlorine gas, right? And then we have the sodium ions left in solution. The sodium ions will move across the diaphragm, right? there into the other compartment, right? Where we're gonna have the releasing of hydrogen gas and leftover hydroxide. The sodium and the hydroxide, right, will actually mix to create sodium hydroxide, and that's how we have that, right, as a component or a product. All right. So chlorine gas at the anode, producing at the anode. Then we have hydrogen gas being produced at the cathode, right? Then we're gonna have hydroxide ions and sodium ions left in solution that will bond to produce sodium hydroxide. That is what is happening there. All right. So the anodic reactions, right? The oxidation at the anode. We should remember. We should know what's generally happening here. All right. So the primary reaction at anode is going to be the loss of electrons from the chloride to produce chlorine gas. All right. You also do have a minor, you actually have a minor reaction happening here as well, right? So you can actually have hydroxide, right, being, well, producing water and oxygen as well as free electrons, right, at the anode. But the primary reaction, right, is the production of gaseous chlorine at the anode, all right? So that's what we have there. At the cathode now, the primary thing that we tend to see now is the releasing of hydrogen gas from the electrolysis of water. Alright? So we have that there. Make sense? Or the oxidation of water, not the electrolysis, the oxidation of water. Alright? So we have that there. We have the production of hydrogen gas there at the cathode. Okay? And as we say, right, the chlorine gas is going to be produced, hydrogen gas is going to be produced, leaving free sodium ions and free hydroxide ions, right? And that will now combine to create sodium hydroxide, all right? So as we can see here, hold on, as you can see here, sodium ions will come from the anode, right, going across the diaphragm into the solution. And then as hydrogen is being produced, hydroxide ions are going to be produced here in solution, right? We have sodium and hydroxide ions in the solution that will produce now our sodium hydroxide, right? And as we take out the sodium hydroxide, some sodium chloride is going to be in that solution as well. Are there any issues with anything so far? Any issues with anything so far? No? All right. So, okay, so I'm gonna go over it. I'm gonna go through this and then go over it one more time. So we have two more slides going through it, all right? But before I go through it, as you requested, right? What is the anode made of? Titanium, and then the cathode would be steel. Lovely. All right. So we're gonna go through it, over it again, right? So this formation of the sodium hydroxide, right? So we know that we have the electrolysis at two separate areas. And at the anode, right, we have the chloride ions being removed as chlorine gas. So the production of chlorine gas at the anode. All right. At the cathode, right, we have the production of hydrogen gas. Right, at the cathode. So the remaining ions in the electrolyte would be sodium and hydroxide. Right. So these ions do not further react at the electrodes, but they remain dissolved in water as sodium hydroxide. Right. The porous diaphragm prevents the back moving of chlorine and hydroxide, avoiding the production of hypochlorite or chlorate. Right? So we know that hypochlorite and chlorate are different oxidation states of chlorine being present with hydrogen. Right? The diaphragm allows one movement, one directional movement, right, from the area of the anode to the area comprising the cathode. So we're going to look at it once again from this diagram, right? So let's look at it here. What we do is introduce brine to the solution, to the entire cell, right? So we introduce concentrated sodium chloride. Lovely, right? That's what we have there, right? The concentrated sodium chloride. At the anode now, we're going to have the loss of electrons, right? We have oxidation at the anode producing chlorine gas. All right. So that's what we're looking at first. So we introduce the brine, then we oxidize, right, the sodium chloride generally there, or the not the sodium chloride, but the chloride at the anode to produce chlorine gas. That is what we have there, which is fine so far. All right, fine so far. Okay, lovely. So you have that there. We produce chlorine gas. Now, what's happening on the anode side of this entire cell, right? We have chloride being released as chlorine gas at the anode, right? Leaving the sodium ions. Sodium ions will not react at any electrode. It will now pass through the diaphragm, right? So it passes through the permeable diaphragm bridge, right? So note, if the sodium, right, or generally the ions, right, will pass only one direction through the diaphragm, right? So they will pass from the chamber containing the anode to the chamber containing the cathode. That is it. It will not go back way. It will not go the other way, right? So now sodium ions are entering the area containing the cathode. We know at the cathode now, we're gonna have hydrogen ions, right? This is due to the autoionization of water. Water will naturally ionize into hydrogen ions and hydroxide ions. Lovely. At the cathode now, the hydrogen ions are gaining electrons, right? And being produced as hydrogen gas, right? Or they leave the system as hydrogen gas, leaving now a higher concentration of hydroxide ions in solution. Now the hydroxide ions and the sodium ions are free in solution, right? And they will form sodium hydroxide, right? Or many of these diagrams will describe that as caustic soda. That is the colloquial name for sodium hydroxide, right? The sodium hydroxide now will be captured. So that is what we capture now. We capture the sodium hydroxide, right, as runoff from the reaction, all right? And then sometimes you'll have that dilute amount of sodium chloride left, all right, or brine left that will actually come off with the caustic soda. So that is what's happening here. So we know that the anode is made of titanium, the cathode is made of steel, and here it now states that the diaphragm is made of asbestos fibers and other types of polymeric materials, right? But usually we speak specifically to the asbestos that the diaphragm is made from. Alright? So we know that diaphragm separates the anode and the cathode components but allows ion migration, right? From the area of the anode to the area of the cathode. Right? So we must know those things. We must know how to draw the diagram. We must know the reaction occurring at the anode. We must know the reaction occurring at the cathode. Right? We must know what the anode and the cathode are made of. We must know what the diaphragm does and what it is made of. Right? And we must link everything to the production of sodium hydroxide. That is what is required of us. Nothing else is required. Alright? So here's a simple diagram. So a lot of persons love complaining about, oh, they're not artists. That's fine, right? They're not artists. But we can draw this simple diagram. It's the simplest diagram that can be produced here. Alright? And then you label your anode, your cathode. You show your ions in solution. You will show your sodium ions being moved across the diaphragm, etc. Alright? Are there any questions or concerns here? Alright, go ahead. Okay, so why the water level is lower? Alright, hold on. Alright, so let's look at this here. Right? When we actually input the brine through this area, right? So we'll input the brine and fill up this entire area, right? Why the water level is low on this side is because of the diaphragm, right? So diaphragm doesn't allow everything to go through, but we're gonna have the trickling of some of the solution and some major ions being moved through, right? So there are less things on this side than on this side. There are less things on the cathode side than on the anode side. So that's why the level is a little bit lower. Alright? That's just a general thing. there. It's not something that they'll ask though, or it's not something that I see primarily that they ask. All right, but you just need to represent it. Mhm. And also, you are collecting sodium hydroxide and sodium chloride from this side, so naturally you're draining from the cathode side and you're adding to the anode side. So one level would be a little bit higher than the other. So you're constantly draining solution from one side. Alright, so let's have a look here. So managing liquid flow and diaphragm cells. So as I stated now, there's unidirectional flow of brine solution from the anode to the cathode. Right? The diaphragm allows only one direction. Right? It prevents the backflow from creating things like hypochlorite and chloride. Hold on. There's a question? Okay, so Sharifah provided an answer. So you could, okay, so the percolation rate here, sure. Mm. Alright, so you can have a look. I think the person who asked, you can have a look at what Sharifah has in the chat there. Alright? So said the percolation rates are controlled by maintaining a higher liquid level on the anode compartment than on the cathode compartment. Alright? Okay, so we're looking at stuff like this. So we're looking at the crucial understanding of how the diaphragm cell works with the unidirectional flow here, right? Preventing an undesired byproducts. Alright, input and output. So we know the input now, right, would be the brine, the output would be the chlorine gas, right, the hydrogen gas, and the sodium hydroxide solution with some residual sodium chloride. Alright? So we must know what goes in, we must know the reactants, what comes out, we must know the products. For every reaction, we must know those. Alright? So post electrolysis and separation recycling now. So the sodium hydroxide solution is contaminated with unreacted sodium chloride. Alright? So the solution of the solution is processed a bit further with the sodium chloride being crystallized out via evaporation and cooling. Right? Recovered sodium chloride is recycled back into electrolysis process, right? So if you have unreacted sodium chloride, we just add it back to the process so it can be reacted, right? We'll also have purified sodium hydroxide that is stored and used as commercial product. Right? So recycling the steps enhances the efficiency and sustainability of the industrial process. Right? So you can't just keep on taking out unreacted chloride and not adding it back. It is more efficient to add it back. Alright? So it's the second cell now here would be the membrane. So the first one, the diaphragm cell. Do we understand the diaphragm cell a little bit more? This is the first one. So we must understand the diaphragm cell and then we'll move on to the membrane cell. I'm not hearing any questions. I'm assuming that everything is good to go. Everything is good to go? Uh, Oh, Cassandra, I am recording it. Alright. So lovely. The membrane cell. Now this looks a little bit interesting. Alright. So really and truly, let's have a look at what's happening here. So the membrane cell is a modern alternative to the diaphragm cell, right? So here we have a selective membrane composed primarily of the polytetrafluoroethylene, right? And it is permeable to cations such as sodium, right? And impermeable to anions, especially chloride, right? So the key functionality prevents the chloride ions from migrating into the cathode compartment, and it allows sodium ions now to pass through to produce sodium hydroxide. So now we have no production of sodium chloride coming out because chlorine is not passing, right? Or the chloride ions are not passing that polytetrafluoroethylene membrane. So the result now is a higher purity of our sodium hydroxide because there's less residual chloride ions getting past. Makes sense? Alright? Hopefully that makes sense. So with the asbestos diaphragm cell, we had some chloride coming past, right? So it contaminates our hydrogen, our sodium hydroxide, right? But with the modern diaphragm cell now, where we use polytetrafluoroethylene, we have little to no chloride ions moving over to the cathode compartment, right? So we have a higher purity of sodium hydroxide. In this case now, a lot of the times we see that a nickel cathode is used, all right? So this is what we have here, okay? Any questions or any concerns? So the diaphragm cell and the membrane cell are essentially the same, right? The only difference is that in the membrane cell, the membrane is made of polytetrafluoroethylene, while in the diaphragm cell, that diaphragm is made of asbestos, right? In the membrane cell, the anode is titanium and the cathode is nickel, while in the diaphragm cell, the anode is still titanium, right? While the cathode is steel. We must be able to catch those differences. All right. We're moving on to. Oh, go ahead. You have a question? No problem. The Kastner-Kellner cell. All right. So we have this as the last cell that we will look at. All right. So colloquially, it's called the Mercury cell. All right. So it's an alternative electrolytic process. So the Kastner-Kellner cell, the cathode is a stream of flowing mercury, while the anode is typically made of carbon or titanium. Right? So the electrolyte is still the saturated brine. They will still take it from the brine. Right? With the cathodic process, we have sodium ions being reduced at the mercury cathode. Right? So we end up with sodium in its aqueous format, right? Being formed into sodium liquid, right? And this is an amalgam. So when mercury tends to create multiple amalgams with different metals, right? So the newly formed sodium metal dissolves in mercury, right, forming a sodium mercury amalgam, all right, which we normally write as sodium slash mercury there, all right. So a lot of persons kind of get thrown off by this because they never really think of like metals dissolving in things, but metals do dissolve in other metals, right? We have germanium as well, that some things can dissolve in germanium, right? But in this case, we're looking at mercury, all right? So this reaction prevents the highly reactive sodium metal from immediately reacting with water in the solution, all right? So we have something like this, all right? So clearly coming from a book, right? So we have the different partitions here, right? So let's go from left to right based on how we read and stuff, right? So let me just use the laser pointer. So first of all, now, right, we're having the water come in, all right? So hold on, let me allow that spirit to enter the meeting. All right. So this is a depiction of the cell that we're using, the mercury cell. All right. So we have a cathode here, an iron cathode in this case, right? I have two carbon cathodes in this case. All right. So we have the water that comes in, splitting the water, right? Um, the water with the sodium chloride in it, right? The chlorine will be released at the anodes, right? While the sodium will be dissolved in the mercury as an amalgam, right? So what we're doing is producing primarily chlorine gas and some hydrogen gas, right? And really and truly obtaining the mercury amalgam, right? The mercury amalgam in the presence of an iron cathode, right, can be used to produce some sodium hydroxide, all right? But really and truly, we're producing primarily chlorine rather, gas, right? Chlorine gas. That's primarily what we're producing, all right? So through this cell, or we can look at this diagram here, right? I think this diagram would be something that we tend to look at a little bit more because there are different ways in which we can depict it, right? So probably this diagram would be a little bit more friendly to you guys, right? Where we have the brine coming in, right? We have the carbon anodes here, right? And when we have the production of chlorine gas going out and the brine going out, while the sodium is dissolved into mercury, right? Creating the sodium mercury amalgam, right? So we have that there. So at the anode, we have the production of chlorine gas, and at the cathode, we have the dissolution, right, or the dissolving of sodium into mercury to produce the sodium amalgam. All right, so that's what's happening there. Any major issues with this? So what we're seeing is that we have the production of a sodium amalgam and the production of chlorine gas. So the primary product here is chlorine gas. All right. So if we want to produce, if we have a reaction that we need chlorine for, and we don't necessarily need sodium hydroxide, it makes more sense to use this process to produce primarily chlorine, as we will not be using sodium hydroxide. But in other cases where we have chloroalkali production, we'll need this production of sodium chloride, well, not sodium chloride, the production of the sodium hydroxide as well as chlorine gas. So we tend to use the membrane cell or the diaphragm cell for those. But if we only need chlorine, it is preferred to use the Castner killer cell, or what we call the mercury cell. All right. So this is what we have here. Which is this cell under? Which is what specifically? We have three cells in the chloralkali industry. The diaphragm, which has a asbestos diaphragm, right? The membrane, which has a PTFE membrane, and we have the mercury cell, right? So it comes under the chloralkali industry. All right, or chlorine. All right, so we have that there. So we have the advantages and disadvantages of the different cells here. So the mercury cell, the diaphragm cell, and the membrane cell. All right. So in the mercury cell, we require higher voltages, require higher purity of brine, and mercury released in the environment is highly hazardous. All right. So looking at stuff like that. For the diaphragm cell, alkali is slightly impure, and and asbestos is a carcinogen. So you can look at those things that we have in the cells there. Do we know what a carcinogen is? Okay, lovely. So it can cause cancer. It's a cancer-causing agent. Alright? The membrane cell now, the brine must be of high purity, and the sodium hydroxide is lower in concentration there. Alright? But we have this, right? So advantages and disadvantages, we must note these. Alright, for this topic. So moving on, right, the amalgam and red flags with that, right? So we must note the dangers that this may have an environment. So the amalgam is continuously pumped into a separate chamber, which reacts with water to produce sodium hydroxide, right? So that is in this larger diagram here where we have the amalgam being pumped to produce sodium hydroxide. So we can produce sodium hydroxide easily, right? Mercury is now really is recycled back into the main cell, right? Though it produces high purity of sodium hydroxide, the use of mercury poses serious environmental and health risks, leading to the phasing out of in favor of diaphragm and membrane cells. So we don't tend to use this cell anymore, even though it is really effective because of the use of mercury and copious amounts of mercury. Right? We tend to phase it out, or it is being phased out, as it really poses serious environmental risks. All right. The industrial importance of chlorine now, why we would produce so much chlorine. Chlorine is used in bleaches, right? Sodium perchlorate, which is a powerful oxidizer, using whitening clothes, removing stains, disinfecting surfaces, sterilizing water. We also have the production of polyvinyl chloride, PVC, used in insulation pipes, window frames, clothing, and bags, right? Chlorine is also used as a solvent in many of our chemical reactions in chemistry unit 2, right? Production of chloroform, right, which is tetrachloromethane, which is a great solvent, right? Many phased out due to its environmental risks, though. So many of the different solvents that we use are phased out. So primarily use chloroform now as the primary solvent, right? We also use chlorine in aerosols and refrigerants, so CFCs, right? Once widely used in sprays and refrigeration, right? And it's now banned due to the ozone depletion, which we will look at now in actually in atmospheric chemistry, right? Some aerosol products still contain CFCs, by the way, right? So people who love using air sprays and air conditioners and stuff like that, they may contain CFCs which are detrimental to the health of the atmosphere, right? So also using anesthetics, right? For example, halothane, which is chlorine containing inhalation anesthetic, right? Which is still in use, right? So anesthesiologists may use chlorine containing compounds, right, to really use medically, I guess. All right. So environmental impact now for the diaphragm cell, we know that it has asbestos fibers, right? If poorly maintained, we have asbestos inhalation, which can lead to lung cancer, right? Over long-term exposure. With the Kastner-Kellner cell or the mercury cell, mercury contamination of air and water, right, is a major risk. Mercury bioaccumulates, meaning that harmful aquatic life, it is harmful to aquatic life and human health, right? We know what bioaccumulation is from CSEC biology and from Cape Biology Unit 2, right? So we should know what that is. What is bioaccumulation? Anyone? Do we know what bioaccumulation is? Or if you don't know a specific definition, explain to me what we mean by bioaccumulation and how it may be harmful. hmm Okay, so lovely. You're on the right track, right? So looking at the accumulation of these things in the environment, right? What we're saying is that if mercury, oh, go ahead. I think someone is speaking. My apologies. Was someone speaking? All right, no problem, right? But what we're looking at now, if mercury enters the environment, as we state, right, organisms in lower trophic levels may consume the mercury, right? And then organisms further up in higher trophic levels will consume those organisms, increasing the amount of mercury present in populations, right? So bioaccumulation speaks to the fact that toxins, the concentration of toxins will increase as you go up trophic levels, right? So if mercury is introduced into the environment, right, it may be caught up in plant fibers, it may be caught up in algae, etc., which fish may eat, which larger fish may eat, which humans may eat, right? So as you go up the food chain or go up trophic levels, right, the concentration of these harmful metals, right, will increase. So it will actually increase. It may not be very harmful to some animals, right? But as you consume a large amount of those animals, it may increase to a deadly amount in you. All right. So I'm not sure when persons understand like food and nutrition and stuff like that, right? But mercury is found in fish, right? Meaning that there is a substantial amount of mercury contamination in the ocean, right? For us to now know mercury as a trace element in fish, right? So we must be careful of these things, right? So mercury bioaccumulates, harming aquatic life and human health here. We also have PVC production, right? PVC are plastics, non-biodegradable plastics, which breaks down slowly and pollutes water sources. We also have weathering, so it releases toxic chemicals into the environment, right? So PVC burning as well creates dioxins, hazardous compounds linked to reproductive and developmental harm, right, and long-term health risks. So you can look at that, the environmental impact of the chloroalkali industry, right? And that really brings us to the end. So really and truly for the chloroalkali industry, we are to discuss diaphragm cells, right? We are to discuss membrane cells and the Kastner-Kellner cell, which is a mercury cell, right? We must know the differences between the three. We must know the oxidation and reductive processes in the three. We must know the advantages and disadvantages in the three, right? And we must know the importance of chlorine products and the environmental impact on the environment of the chloroalkali industry. And that brings the topic to a close. Are there any questions or any concerns?